Hello again, everyone. Welcome back. We are gonna give people a few more minutes to finish up their lunch, go to the restroom, etc. So I should start at 2:20.
Make sure you download the demos on module 3.3 and upload in NanoHub if you're using a NanoHub.
Yep. And also the Avascular Tumor, the completed code that is a bit different from what I did in classes there, and what I did in class so far is also there. And just a reminder, we are being recorded and live streamed to YouTube. Okay, so it's 2:20 right now in Indiana. Once again, I should remind everyone that we are being both recorded and live streamed to YouTube. And we are gonna get back into module 3.2, part 2 of it. Part 1, we've built that simulation there that there's something about it that just looks nasty to me. I really like it. And what we did before was we changed cell behaviors based on the measured concentration. And now we are going to have our tumor cells actually eat up from this nutrient field here, instead of just letting it decay inside of the cells. Okay, so getting started. Let me actually go back a bit on what we did. So what we did here in the step rules was we have here the constraint initializer, where I'm initializing the threshold numbers. The proliferating quiescent transition, right now I'm setting it to 80% of 100 divided by half of V. The quiescent back to proliferating, I set it to be just a bit higher than the other one. And finally, the transition to necrosis is 100 divided by E. I think if you disable the cell borders, it's disabled on all of the visualizations, unfortunately. We've also set ourselves to be 64 voxels big, with a lambda volume of 8. And then here in the growth step, we are doing all of the magic. We are telling CompuCell to look for this cell dictionary called conc to make it easier to visualize what concentration we are measuring inside of the cell. So it looks similar to the nutrient field, but it's clearly different. It's discrete, while this one is smooth. And then in the step function, we are asking for all of the values of the nutrient field. Then we are going over all of the proliferating cells. We are measuring the concentration at their center of mass. We are saving that to the cell dictionary. That's what allows us to see this field here on the right. And then we are checking if that concentration is below our transition threshold for quiescence. And if it is, the cell becomes quiescent. If it's not, it's still proliferating, so it grows by a little bit. And then we are doing something similar for the quiescent cells. Again, measuring the concentration, saving it. If the concentration is above the threshold to go back to being proliferating, and becomes proliferating again, and it also grows by a little bit. And if the concentration is below the necrosis threshold, we are setting them to be necrotic, and we are setting their target volume to be 0. So here we have less than, because we are transitioning from proliferating to quiescent, and proliferating is more demanding on the cell, so they need more nutrient. So it makes sense that when it go down in concentration, we go to quiescence. While here we are asking if we can go back up to be proliferating. So that's the switch here. And now what we are going to do is, instead of using the measurement at the center of the cell, we are going to have the cell's uptake from the nutrient field, and we are going to use that as a basis. So, as usual, Twedit knows how. Although in just a minute, Twedit won't know how. But that's spoilers. So what I'm going to do is I'm going to come here before my first loop. And I want to do uptake. So here in CC3D Python, we have secretion uptake. Uptake is negative secretion from the point of view of the computer. And I'm going to uptake inside the whole cell. So again, before the loop, CC3D Python secretion uptake inside cell. And now we have the commands we need. So first, it's creating this object secretor, and that object is responsible for the uptake. And we can see that to have the cell uptake, we call this function of secretor, passing to it a cell, the maximum uptake the cell can make, and the relative uptake. So this function here, as a reminder, looks like this. So while the concentration is above this maximum, it's only going to take the maximum. And if it's below the maximum, it's going to take a percentage of the concentration that is there. But here we don't, well, if we try to run, we would get a complaint of cell used before assignment, because, well, there's nothing here saying cell equals something, while here we have. And one point that I'm going to make is that the name cell here is not important. I could very well have ASD in cell list, and ASD would still be cell objects. After all, we are iterating the cell list. This handle here is important. So for this loop, I'm gonna make my life harder. Don't do this. And have ASD instead of cell. But again, don't do this. I'm just making my life harder because I don't know. And so what I'm going to do is have the secretor function be inside of the loop over the cells that we want to do. But I actually need to specify what field I am talking about. And the field is nutrient, which I called NUTR. And then I'm gonna cut this command here to be inside of the loop. And indentation matters, so putting that in. And on my slides, I have that I set the max uptake to be 1 and the relative to be 0.1. So I'm gonna keep that. And in here, so if I try to run this, I'm gonna get an error right here. Just to prove it to you, I stop it here, play. There you go. But if I do this ASD now, things should be good, hopefully. Otherwise, I'll have to eat my hat. And now the proliferating cells are going to line 56. Yeah. So yeah, line 56, I had cell instead of ASD. And that's where it complained. Now I have ASD, line 56. And it works. But I don't want only the proliferating cells to be eating up nutrient. I also want the quiescent cells to be eating up nutrient. So I'm just going to copy over that command to be down here. And in here, it should be cell for me. I'm not changing this cell to be ASD, and please do not change any cell to be ASD on your code. Now we have both cells eating up nutrient. This does mean that the chemical change profile is going to be different from before. Before we were only letting the chemical degrade inside of the cells. Now we are actually taking out of the chemical food inside of the cells. So we need to adjust our thresholds again. And this would be kind of trial and error. Thankfully for you, I already did the trial and error, so I know what to do now. I mean, we could leave it as is, but I think it becomes more interesting if we now change, instead of having 80% here, we're going to do 50% of that number on the right, and we are also gonna diminish the necrotic threshold by 50%. So again, me just gonna let this run while I talk. What I did was first asked to edit how to do secretion. I came before my loops, went to CC3D Python, secretion uptake inside cell, the whole cell. It pasted both this command, but without the field name there. I put that in, and it also pasted this command with some other numbers there. So I moved the command from back here to be inside of the relevant loop. I set the max to be 1, the relative to be 0.1, and I also have the same command down here. Okay. So now how do we visualize how much the cells are actually eating? Well, this is one thing that Reddit doesn't know how, for some reason. It's a simple change to this uptake function. We just need to add total count. And if you notice here, the first letter of each word besides the first is capitalized. This is called camel case. And different programming languages have different standards for when to use camel case and when to use snake case, which is using underscores to separate words. And in this case, it's camel case, so we add total count like this to the end of the simulation. And we actually need to get the results from that function. So I'm going to have R equals secretor dot uptake inside cell total count cell max relative. And I'm going to have the same thing for my quiescent cells. And now to visualize this, I'm going to replace this extra field that we created before. Instead of having the concentration at the center of mass, I'm going to place this before we actually do the uptake. And what I want is the results from the uptake. So I'm going to replace the concentration at COM by R dot amount. And I'm going to do the same thing down here. There we go. So now if I stop this and rerun, and we go. I change this to be that conc field that we had. And I keep this with the nutrient and run. What is going on? That I didn't expect. What did I do wrong? Yes. Comment out the uptake. I have an idea of what's going on. Right. I shouldn't have replaced the value here at conc. I should leave that as concentration at center of mass, because I'm using conc here to change for the thresholds. And so instead of leave this here, and what I'm going to do instead is I'm going to create a new cell dictionary, and I'm going to call it something else. I'm going to call it upt for uptake. And this one, I'm going to have r dot total count. And same thing down here. And then to actually have CompuCell track this, just need to copy this command and tell it to search for UPT. So I asked to edit how to do the uptake. Then I told that I'm looking for the secretor object for the nutrient field. And in my proliferating and quiescence loops, I have here the result of the secretion saved to R, and the secretion is being done inside of the whole cell with a maximum of 1 and a relative uptake of 0.1. And then I'm putting the actual result, which is not R, but R dot total count, dot count, to this new cell dictionary UPT. Now I go. It's not right. I should read my slides. It's not dot count, it's dot amount. And now if I tell it to run, it should work. Good. So if I change this field here to be UPT, we can see that all the numbers are very negative, because uptake is defined, as far as the computer is concerned, as the negative of the secretion. That's why we have the minus. And one thing that is not that noticeable here using the extra field, but is noticeable if you print the results straight to console is that the uptake is about the cell volume. Because uptake inside cell total count, this maximum and relative. So for the secretion, I would point you to the manual. And I had total, its total amount period. I just, my brain got confused. But the results is about the cell volume, because this maximum and relative is for each pixel of the cell. And since we are telling it to have a maximum uptake of 1, the maximum uptake result is the cell volume. And that gives us an easy way to normalize the uptake based on cell volume and so on. Yeah, here I have it. So before changing, yeah. So the next step here would be to change the growth based on this uptake. But before we do that, I actually want to change this ifs to be based on the uptake instead of being based on the concentration at the cell center. So thankfully, with the parameters that I used, the result of the uptake is going to be the cell volume. So what I'm going to say conc is instead of being the result total amount, it's going to be uptake is negative because it's reverse of secretion, and secretion is positive. It's going to be the absolute value of the result. That way you get rid of the negative. And I'm going to divide that by the cell volume. And that way, this number here, which is the concentration at the center, is going to be similar to this number here, because this number here is the average concentration of the cell, while here is the concentration in a single point of the cell. So they should be about the same. And I have to do the same change down here in this other conc with my quiescent cells. And if I run this, I'm gonna get an error because I made my life harder by changing cell here to be AST. So there, absolute, for the absolute value of the number. I could, instead of doing abs, I could have done just the negative of the number. In this case, it's the same thing, but yeah, good catch, man. So hopefully now things should still behave more or less the same. Probably. We're gonna know in a second if I have that mistake. Yeah, okay. Have something wrong. Joseph might know already what I did. Yes. Yeah. Yeah, so this should be down here. And it still may not work because I didn't test this before. So live coding is always a thrill and things would never go right. So if this doesn't work, I'm just gonna roll back the changes and use the central, the central value. Not really sure why it did this didn't work, but I'm not gonna waste time from the class with something that doesn't work. So Sorry to make you mess around with your code and then undo everything you did. But keep the cell dict count to be the concentration at the center of mass. But if you wanted to change the thresholds to be something related with how much the cell could eat up, that's the general idea. You'd need to fiddle with the thresholds and check what exactly are the results of the uptake and so on. And doing that, it's easier on the local installation because here we don't have the terminal, while in my, if you use CompuCell locally, it's going to open a terminal window that has all the prints. Yes, if you wanted plus before. Not sure I understood the solution, but if you might try it. Plus before. Ah, okay. So keep updating the concentration. Yeah, maybe. But I'm gonna keep things working. So the actual change we are going to do is we're gonna change the growth. Instead of being a fixed amount, it's going to be a part of the nutrient. So I'm assuming that part of the nutrient that the cell consumed is used to keep the cell alive, and any surplus it has can be used for growing. So here inside my loop over the proliferating cells, in the else, which means that the cell is still proliferating, I'm gonna, instead of hitting plus 0.5, I'm gonna have plus 0.5 times the absolute value of the uptake amount divided by the cell volume. And as I mentioned, this number here is going to be about right. Nice. Good. Glad that the solution was easy. And I have to remember to do the same down here. So now, if I run this, yep. Keep forgetting that I'm making my life harder. This is why I told you not to do this. But I thought it was an important point to make, that cell is not special. You could do ASD, you could do flower, you could say cat. And cool, the simulation still works. It actually looks remarkably similar to before, but that's kind of part of the point. And the next exercise is doing what tumors do best, which is mutating. In the slides and the code, full code that I uploaded, I'm mutating a lot of stuff of every cell. I'm letting every cell mutate their thresholds, so they could be more resilient to lack of nutrients. I'm mutating how much they eat, so a cell that eats more has a competitive advantage. I'm changing how much they grow. A cell that grows faster also is more competitive. But in class, I'm just gonna mutate one of their attributes. That way we can see more fun things. And the attribute that I'm gonna mutate is growth. So the first thing is, instead of having growth be this hard-coded number here, what I'm going to do is come to the very start of the step function, and I'm gonna re-enable this loop that I disabled way back at the start of the simulation. but I don't want the cells to grow here, so I'm gonna get rid of that, or just keep that part commented out. And I'm gonna say that every cell now is gonna have a dictionary attribute called growth, which is how fast it can grow. And I'm gonna set that to be 0.5. And since I'm already here at the top and I'm near the init function, I'm gonna create one more extra field. And this one, Compusa is gonna look for the keyword growth. And so instead of hard coding, well, it's still hard coding and it's here, but this loop, the way it is gonna nullify any mutation, because for every step, I'm going through all of the cells and resetting their growth to be 0.5. So I only really want this to happen in the first MCS. So I have two options for MCS 0. I could either say if MCS equals 0 and put this loop inside of the if, or I could remember that 0 is equivalent to false in Python and say if not MCS. Either works. To me, they are both equally clear, but personal preference. So if MCS is 0, set that growth. And now what we are going to do, and we are almost done, is, well, first, remember to replace the halves here by self-dict growth. And then we are gonna have mutation happen when the cells divide. So we are gonna go all the way down to the mitosis tuples that we forgot about until now. So after clone parent to child, we are gonna have our cells have a really high mutation chance. We are going to have a mutation chance of 90%. So if numpy that I've imported already, dot random, dot uniform, because I want a uniform distribution between 0 and 1, is less than 0.4, this gives us a 90% mutation rate. Then I want the cell dict, the growth dict, which is here, to change by, well, in the slides I'm saying plus or minus 10%, but let's be more aggressive just to make things more visual. So cell growth is going to be multiplied by, well, it's going to equal itself multiplied by numpy.random.uniform again. But in this case, inside of uniform, gonna change stuff by plus or minus 50%. So uniform from 0.05 to 1.5. Well, and here it shouldn't be cell. It should be parent cell for the parent cell. And then I'm gonna copy the whole if, and the child cell can mutate independently of the parent by a different amount, and it may not even mutate. And this is pretty much it for the lecture. Now you know how to do a vascular tumor and how to do cancer mutation. What else could you want? Cell reference before assignment. Did I forget that I was using ASD? Yes, I did, as usual. Let me change this one to be growth. And for now, everything is in half because the cells haven't had a chance to mutate yet. But as soon as they mutate, we are gonna see this one. Well, actually, let me do different. Let me change this to the cell field and this to the growth field. And we already have cells that are growing faster than others. And we are probably gonna see those cells surviving more and become the dominant strain in the simulation. Yep. Let me go back to the code. So I went all the way down to the mitosis steppable in the update attributes. After we clone everything from the parent to the child, I'm giving both the parent a 90% chance of mutation and the child a 90% chance of mutation. Well, each of the siblings really, right? So rolling a dice between 0 and 1, and if that's less than 0.9, then changing the growth by multiplying it by some random number in between half and 1.5. And same thing for the sibling. That's it for me. And I'm going to upload this to the Google Drive as well in just a second.